continue. Let's look at the motion map here. If the motion map below shows an object that is moving to the right, can you tell if it is speeding up or slowing down?
I think it's speeding up.
How do you know?
Well, the distance between each dot per second, it's getting bigger. So the distance per second is getting bigger. So the object is moving faster per second.
Faster and faster per second. Very good. So what we want to do here is that we want to connect it to the force that this object is experiencing as a function of time. Do you think this object is experiencing no force at all? Balance forces, just like the ball in space or the parachuter? Or do you think there is a force on this object? And if there is a force on this object, what is the direction of that? Do you think it's to the right or to the left?
I think there's a force going to the right because it's moving faster to the right.
Very good. So this object probably is experiencing a force to the right. But can it experience a combination of forces just like this? Is it possible for this object to experience a combination of forces like that?
Yes.
Okay. So what is special about this force diagram? We have a force to the right that is blue, and there's a smaller force to the right. What is special about this force diagram? What can you tell about it? Whatever comes to your mind.
Well, the blue force is bigger, so it might cancel out the red force.
Cancel it out completely, or there will be a leftover force, do you think?
There would be a leftover force to the right.
There will be a leftover force to the right because, what's the reason?
Because when you cancel out the red force, there's still part of the blue force that's left.
Very good. So do you think the blue force is larger than the red force, and that's why there will be a leftover force there?
Yeah.
Okay. So that leftover force, we call it a net force. Net force means combination of forces on the object. And for this particular case, you can see that the leftover force could be a force like this green force, right?
Yeah.
And an object that is moving to the right and speeding up is experiencing more force to the right. Okay. So can you draw your own force diagram on this dot? What do you want to do? If I draw one. Do you think this is acceptable? This is a force to the right?
Yeah.
Right? Okay. So let me see. Do you want to draw one?
Okay.
Okay. What color do you want to draw it with?
Yellow.
Yellow. Okay. So let's say if I have a force to the left, let's say friction force or something like that. Let's draw it in a different size so that it's different than the red one maybe. Okay. So maybe something like that. Okay. So what would be the force to the right so that leftover force would be the same as the green force? Do you want to try that?
Okay.
Okay. How far do you think you should go?
About there.
Very good. So that would give you the same net force as the green force, and that would speed up your object the same way as the green force or as the combination of forces like that, right?
Yeah.
Do we understand this? Is this clear? Maybe? Okay. Let's continue. Okay, so pay attention to this one. This is an object that is moving to the left. What do you think is it doing? Let's just see. So this object is actually moving to the left. Do you think it's slowing down or speeding up?
Slowing down.
How do you know?
Because it's getting the
distance?
length per second, it's getting smaller.
Smaller and smaller, right? So what do you think the amount of force, not the amount, but what's the direction of force on this object? Let's say there's a ball that is coming towards you and you want to stop it. What's the direction of force on it? Would it be to the right or to the left?
To the right.
To the right. Very good. So this blue force right here could be a force diagram for that, right? Do you want to give it a try for this example? Do you think if I draw, let me draw one force. If I draw, let's say, a yellow force. Oh, I don't like this. I do this a lot. Okay. If I draw a yellow force of this magnitude, this big, how much would be the opposing force so that it would slow it down so that you get the same amount of force as the blue force? How much would it be? Do you want to draw it?
Yeah.
Okay. Do you want to draw it in red?
Sure.
Okay. How far do you think you would go? Maybe that much?
Yeah.
So an example of that would be a baseball is coming towards you and you stop it by applying a force in the opposite direction of motion. This is a little bit. So if you apply a force in the opposite direction of motion, you would slow it down, right?
Yeah.
Okay, let's practice with this. This could be a little confusing, but let's practice with this. So think about shooting a hockey puck on ice, okay, with a hockey stick. So we choose ice because after you hit the hockey puck, there will be no friction on the puck, right? What's so special about that situation? Do you want to connect it to things that we have talked about already?
There's low friction on the ice.
Yeah, so low friction or no friction at all, but we have done experiments before. We have done thought experiments here before that are similar to this problem. Does it remind you?
It's kind of like the ball in space experiment.
Ball in space experiment, where after you release the ball, what happened in terms of forces and the motion of the ball?
The ball moved at a constant speed because there's no force to stop it.
Very good. So there was no force acting on the ball and the ball was moving with a constant speed. So I choose this example because after you hit the hockey puck, there would be no friction on the puck and the puck would move with a constant speed with no forces on it. So that's very good. But here we have to pay attention to two different situations, right? The first segment is when you are actually hitting the puck. So the stick is in contact with the puck. In that duration, is the stick applying a force to the hockey puck? Is there a force acting on it?
Yes.
Yes, so there is a force acting on it here. But after the hockey puck leaves the stick, is there a force acting on it?
No.
No force at all, right? So you have to distinguish between those two different situations. When the stick is in contact with the hockey puck, what would be the direction of force on it? What's the direction of it?
The way that the stick is hitting the puck.
Mm-hmm. Yeah, so in this case would be to the right or to the left. Would be to the right, for example, in this problem, right? So actually, we skipped the motion map. So let's just look at the motion map. If the hockey puck is moving to the right and some force is acting on it, if I draw the first 2 points for the motion map, how do I draw the rest of these? Would they get farther away from each other or closer together? Let's say if you apply a force in this direction, in this particular case, how does the motion map look like?
It would be faster.
Okay, so how does the motion map look like then? Yeah, it would get faster and faster. Very good.
It would be more spaced out.
So I have to draw these as if there is going to be more and more space between them, right?
Mm-hmm.
Right. Okay. So the direction of force in this case would be, for example, to the right, right?
Yeah.
Okay. So let's say after the puck has left the stick, how does the motion map look like?
It would go at a constant speed.
At constant speed because
there's no friction on the ice.
Yeah, no force at all, right? In this case, we are assuming there's no force at all, right?
Yes.
Okay. So let's see. So we are kind of practicing with this a little bit more. In this case, let's just practice with let's say you're hitting a ball. So the reason that I'm repeating this is that I want you to distinguish between two different scenarios, right? When you're hitting a soccer ball, there are two different segments here. When your foot is in contact with the soccer ball, is applying a force to it, right? When you apply a force to it, what happens to the soccer ball? And we are trying to draw the motion map for it. So right now in here, let's say the ball is going to the left. What does it look like? I'm drawing the first two dots in the motion map. As it goes to the left, what happens to it if you're applying a force to it? The dots,
it goes faster.
So when it goes faster, what happens to the spacing between the
it gets more spread out.
More spread out. So what does that tell you about the direction of force on this object?
The force is larger to the left.
To the left. Very good. Or it can be just one force to the left, right? Mm-hmm. Very good. Okay. So after the ball leaves your foot, let's say you are in friction. This case is different than the hockey puck on ice. So this ball is experiencing actually friction, which is in opposing direction of motion. What do you think is going to happen to the motion of the ball?
It's going to slow down.
Slow down. So let's say it was moving this much before, right? And then how does the motion map look like then?
It starts getting closer and closer.
Closer and closer together, right? What if the ball stops, right? It gets closer and closer and then stops here, maybe somewhere here, right? What would be the direction of force on this, you think? What would be the direction of, friction force, for example? Would it be to the right or to the left in this case?
To the right.
To the right, that's correct. Okay. So the motion map and force have relationship to each other, right?
Mm-hmm.
So if the dots of in the motion map are equally spaced, you have either no force acting on the object or you have balance forces acting on the object, right?
Yeah.
But if the motion map dots getting closer or farther away from each other, what can you say about the force diagram? Is it balanced or unbalanced?
Unbalanced.
Unbalanced, right?
Because a balanced one would be equal forces on each side.
Right, right. So that's a distinguishing fact between balanced forces and unbalanced forces, constant speed and non-constant speed. Later on, we learned that non-constant speed is acceleration, and that is directly proportional to the amount of force that you apply to the object. So in the second book that is called Dynamics, we really dive down into these concepts, understanding how the force and acceleration are related to each other. But this is a good way of starting. And also in here, I'm trying to distinguish between different portion of an event, right? So when you're kicking a ball, there are clearly two different portion of the event. One is that when the foot is actually hitting the ball, right? So the direction of force in here is clearly different than when the ball is actually moving on its own and stopping by friction force, okay? So I want you to distinguish between these different segments. So let's look at this motion map right now. Let me just highlight it so that we can see what we are pointing at. So if you look at this motion map, if you don't know the direction of motion at all, do you know if it is speeding up or slowing down?
No.
No, you don't know?
Yeah.
Okay. So we don't know. That's true. So without knowing the direction of motion, we don't know if it is speeding up or slowing down. I'm going to give you a couple of scenarios, okay?
Okay.
What if this object was moving to the left? Was it speeding up or slowing down?
Speeding up.
Right, because if it was moving to the left, look what happened to the motion map dots. The distance between them increases and increases, right? What if it was moving to the right?
It would be slowing down.
Slowing down, very good. So this object could be slowing down or speeding up. We don't know. But we know something for sure. We know the direction of force on it, okay? Try to guess what's the direction of force on this object. Think about it.
To the left.
How do you know that?
Because the force is acting on the left, which is making it go to the left.
So it's not because it's moving to the left that the force is to the left.
Because it's speeding up.
Speeding up to the left. Very good. So this is very, very important. So if the object was moving to the left and speeding up, right? Let's say this object was moving to the left and speeding up. The direction of force would have been to
the left.
To the left. What if this object was moving to the right and slowing down? What would be the direction of force?
Also to the left.
Also to the left. Does that make sense, what we just said?
Yeah.
Okay. So you have seen this example in real life before. I'm giving you one example. So if I'm hitting a tennis ball with a tennis racket, I'm applying a force to the tennis ball, and the tennis ball would accelerate or speed up. Do you want to give another example, something that is maybe moving to the right and slowing down? Because it would experience the same type of force. Do you want to think about that?
Maybe like a train.
A train that is doing what?
It's slowing down.
Slowing down, right? Or a car that is moving right and slowing down. In both of these situations, the amount of force is leftward.